So when we talk about area under the curve or distance or whatever the problem's talking about, anytime that you're trying to figure out what the units are, if you have a graph or a table or whatever the x units are and the y units, once you find the area, you always multiply the x units by the y units to figure out what the units of the area represents. Whenever we're talking about velocity, like in feet per second and time in seconds, that's why when we do feet per second times seconds, we get feet. Now, in other situations, it might be about population, or it might be the rate of change of dollars or whatever. But we still, to figure out our units, are kind of do the same thing. So here are two other situations that's not velocity in time. The first one is population per year in years. So like maybe we're talking about how fast each year the population is increasing. If I find the area underneath the curve of the y graph in respect to the x graph, then the units I'm going to get are population per year times year. So if I find the area underneath that graph, I get population. On this one, the next one, maybe we're talking about how fast the tank is filling up, and our y values represent liters per minute, and our x values represent minutes. Well, if I have liters per minute times minutes, I end up with liters. Basically what this is saying is, no matter what kind of graph that you have, if this is the graph, and if this graph is f prime of x and this is x, because notice this was population per year, liters per minute. Both of those are the derivative because they're how fast something is changing. If you have the derivative graph and you find the area under the curve, the area is going to represent something about f of x. It's going to represent like the population or the liters or the amount in the tank. And basically it's saying that we go backwards. And one symbol of that is saying the integral of the derivative is the original. And I hope that through everything that we've done that makes sense, that is true. That if you take the integral, which means find the area, except for the parts that are negative, when you do that, you're going to end up with something that represents the original. Now, we also want to be able to explain what it all means. So let's say I have something like this, where v of t is velocity, and I want to say in words what that thing represents. Well, whenever you're talking about an integral, remember that an integral takes into account whether things are negative or positive. If it's above the x-axis, you know that's positive, and if it's below, that's negative. So when you have an integral, this one would represent the change in position from 10 to 13. And I didn't give you any units, but I mean you would say maybe seconds or minutes or whatever the units in this particular problem would represent. It's the change in that. So it doesn't represent the total distance, it represents like where you are now from where you started at 10. And if you're trying to figure out, like v of t is velocity, if you're trying to figure out what this is, you're just thinking about, okay, when I take the derivative of this, velocity is what I get. What is it that when I take its derivative, I get velocity? And so we know that if we take the derivative of position, we get velocity. So this represents the change in position. Okay, here's another one. R of t represents the rate of change of population. And t represents the years since 2000. So if I want to say what this represents, it represents the change in population. Because if r of t is the derivative and it represents the rate of change of the population, then the original equation, like what the integral would represent, represents actual population. So it's the change in population from 2005 to 2014. Which would pretty much tell you if in 2005 if I started with this, in 2014 I started with this, I would subtract those two numbers. Okay, so what if we have one like this? A of t represents acceleration. I don't know if you remember anything about acceleration, but acceleration is the second derivative. So we're taking the integral of the second derivative. And we're going to say that that is in feet squared per seconds, where time is in seconds. So if I say what it represents the change in something. Alright, think about what you would have taken the derivative of to get acceleration. So if acceleration is the second derivative, I would have taken the derivative of the first derivative to get it. Well, the first derivative is velocity, so this is the change in velocity from 2 to 5 seconds. Let's go ahead and figure out what these units would be. If I have a graph and I have acceleration, the y values are in feet squared per second, and the x values are in seconds. And I realize that I wrote that wrong, sorry. This is supposed to be feet per second squared, sorry. So feet per second squared, okay? So if I take the units of acceleration, which are feet per second squared, and I multiply by seconds, I end up with feet per second, which makes sense because if this is the change in velocity, it should be in feet per second. So here's one try problem, and there'll be another one at the end. Let's say that we have 0 to 16 of r of t, where r of t represents the rate of change of height. Where t is in years. I want you to describe what that means. Now, there's one other thing that I want to talk to you about, and it's called average value. The other day, we did a problem where you had to find the area about how fast that person was going, and the area gave us a distance, and at the end of the question we wanted to figure out what his average speed was. And when we did the average speed, we took the distance and we divided by the amount of time that the person traveled. Well, you're not going to be given distance. You're going to be given f prime of x. Or maybe you'll be given velocity. And I want to figure out his average speed or his average velocity. Well, in order to do that, I would need to find the distance, and then I would divide by the time. Well, the distance is represented by the integral. So it would be the integral from a to b or wherever of whatever it is that I'm given, which I'm going to say velocity here. And then to figure out the time, like if A is here and B is here, the time is just the difference of that, so it's B minus A. So this right here is a formula that represents average velocity because I put velocity in the equation. If it just said average value, like average temperature or average rate or average whatever, then you would do the integral of A to B of f of x, whatever f of x represented, and then you would divide by b minus a. So that's a formula that you need to know. It makes sense that that would work. If I find the integral of velocity, that represents distance because that's area. And distance, maybe if we're talking about feet per second and seconds again, distance would be in feet. B minus A would be in seconds, so I would end up with feet per second. Well, that makes sense if I'm trying to find average velocity, that the units I end up are feet per second. Now, there's problems that you're going to be doing related to this average value, so let's do a couple of them. So this is not in your book, it's from an old book. And the first question says, estimate the average value of the rate over the interval from -1 to 3. So here's 3, here's -1, and it's asking us to estimate the average value. Well, I know that the average value is going to be the integral from -1 to 3 of f of x, and then I'm going to divide by 3 minus -1. Well, the integral is just the area, so I'm going to count boxes. And I need to be careful because when I count boxes, I've got some above and some below, so I'm doing those boxes there. There's 2 full boxes. I'd probably put those together and make that a third box. And maybe those together make 4 or 4.5 boxes. Let's just say 4.5 boxes. Now I need to make sure that I'm going up by ones. So I'm going over 3 up 3, so that sounds right. And then to find the average value, I'm going to divide that by 4. And I get 1.125. And if you have something close, that would be okay. And let's go back to the problem just a second. This was the rate, f of x, in thousands of algae per hour. So I found the average value of f of x. So I found the average value of the thousands of algae per hour. So this is still in thousands of algae per hour. So from -1 to 3, we have found that the average value is 1.125 thousands of algae per hour. Next it says find the total change. Okay, as far as the total change is concerned, they're wanting to add all that up, and you know what? That's exactly what I did in B. This here should have been the 4.5, and you don't divide it by the 4. I realize now that I didn't subtract up here. So that 4.4 wasn't right because I didn't subtract since I was trying to find the integral. So let's go back just a second. Up on the top there were 2 and I think 3 boxes. And then on the bottom we said that that was maybe like 1.5. So 3 minus 1.5. So really that was 1.5 boxes. Sorry for that mess up. So you get 0.375 thousandths of algae per hour. The total change, whenever they ask for total change, normally they're asking you like find the total area, not necessarily just how much you are from where you started. And so that's why that would be the 4.5, because that's how many boxes total there are. And you just add the bottom and the top. Alright, so look at 31 real quick. A news broadcast in early 1993 said the average American's annual income is changing at a rate of R of t equals that, where t is in months from January 1st, 1993. How much did the average American's income change during 1993? Alright, it says average in that problem, but average American's income change, that doesn't say average value. So if I were going to do this problem, I'm going to do the integral from, it says during 1993, and everything is in months, so I'm going to do it from 0 to 12 because there's 12 months, and I'm going to put that in there because we're talking about a rate, and if I want to know how much it changed, then I need to do like the area under the curve. Enjoy the music for a few minutes. So basically if I put that in the calculator, you're going to get 485.80. And that would tell you how much it changed from 0 to 12. Now, for your last try problem, I want you to find the average value of the rate during 1993. And that's using your formula where you have to divide by B minus A.